Welcome back, everyone. Welcome to another fun day of learning. Today, we have with us Jerimiah Wright. Jerimiah is a quantum application engineer and research scientist specializing in the development and benchmarking of quantum algorithms for the physical sciences. His work focuses on translating theory into scalable hybrid quantum classical solutions for problems in chemistry and nuclear physics. And Jeremiah also is a Quantum Solutions Launchpad Fellow, and he's been working with us on industry projects for the past year. And now he's also managing his own project. And we're very excited to have him here and deliver this lecture on quantum Fourier transforms and quantum phase estimation. Welcome, Jeremiah, and over to you.
Thank you so much for the introduction. Let me go ahead and get started. Let me just pull up Discord to make sure I can see the questions. Okay, excellent. So yeah, I'm Jeremiah. I'll be talking to you guys through how the quantum Fourier transform and phase estimation came to be. And hopefully by the end of this presentation, you'll get a good understanding of not only the foundations of the algorithm, but kind of the implications and broader sense of how it matters in this industry as a whole. Okay, so the way I'm going to structure this talk is to give you kind of some motivation as to why we are studying these topics, some history behind the Fourier transform and phase estimation as a whole, and then we're going to branch off into directly talking about these operations and how we can define them and how we can think about them. So just starting off with some motivations, quantum phase estimation and quantum Fourier transform are probably some of the most important algorithms for quantum computing. And the reason being is that these are kind of like the fundamental building blocks for greater applications that boast about potential quantum speed up. So case in point, Shor's algorithm is the shining child of quantum advantage, and it's entirely built on phase estimation and the quantum Fourier transform. And it's really important for things like cybersecurity, where you're trying to, factor a large number or trying to prevent people from factoring a large number. And so having an exponential speed up in this quantum field would kind of render that mute. It's also really important for things like quantum chemistry. So say you wanted to find the ground state energy of a quantum system, you would need to perhaps diagonalize the Hamiltonian operator, but Hamiltonians get exponentially large. So having a way of estimating this eigenvalue of this Hamiltonian without diagonalizing it is very powerful. Simultaneously, looking at Hamiltonian simulation, excuse me, is yet another like good application for the exact same reason. It kind of limits how expensive you'd have to simulate this Hamiltonian classically. So these are just some of like the touching points of why this is like a really, really important algorithm as opposed to other things. But there's more. There's a whole list of reasons. Like I think even quantum machine learning uses phase estimation in some case. But yeah, this is like cutting edge stuff. So I think actually before I go on, let's see if the questions work. Have any of you heard of these kind of applications before? Okay, so I'm just checking this live question channel. So yeah, you guys have heard of this. This is case in point because these algorithms are pivotal for transitioning the quantum field into a more public space. So the key hope is that, we can show out these algorithms working and potentially break the barriers that classical computers couldn't. Okay, so to get started, let's talk about some history really fast. And so in order to understand not only phase estimation, but the quantum Fourier transform, it's important to understand where this all began with the Fourier transform. And so in around 1822, I think his name is Jean-Baptiste Joseph Fourier. He developed the Fourier transform, put it here, Fourier transform by Jean-Baptiste. And this kind of led to the development of a lot of things that are still used to this very day, like signal processing and, many, many, many other things. So he kind of set the foundation for the Fourier transform. And later around 1940, but really closer to 1965, someone came along and invented the fast Fourier transform. So this is a fast Fourier transform. And it was Turkey. His name was Turkey, or his last name. And so what the fast Fourier transform, really what it did was that it allowed for this Fourier transform to be used on computers in an efficient manner. So the Fourier transform was rather large, but they were able to calculate it in a reasonable amount of time using this fast Fourier transform. Then in 1994, along came a person, you may have heard of him, named Peter Shor, and he during his famous lecture, gave a presentation on what we call Shor's algorithm. And in Shor's algorithm, what he talked about, oh, I see it right there. Yeah, Holy in Turkey, exactly. And in Shor's algorithm, what he talked about was his famous factorization routine. And a lot of the language that we use today is centered around this talk. So I believe he was the first person to coin the term qubit and many other things actually. But what's really important about Peter Shor's presentation was that in it, he kind of, without explicitly saying it, underlined the fundamental concept of the quantum Fourier transform, as well as phase estimation as a whole. But this is all kind of more like theoretical talk. So later that year, a person named Dan Coppersmith invented or really showed how the quantum Fourier transform could be implemented via circuits efficiently. So this is really what's credited as kind of the first development of the quantum Fourier transform. And it came out the same year as Shor's algorithm, which is pretty impressive. He saw it and made immediate improvements. And then from there, later that year, Alexei Kitaev was showed how you could, well, he essentially formalized the phase estimation protocol. Okay, that's estimation. Okay, and so a lot of this is a little bit confusing because again, Peter Shor's algorithm already used phase estimation, but it wasn't really formalized until Alexei Kitaev came in 1995 to kind of build the language that we kind of use to this day. So he's a very important figure in this as well. Okay, I see you guys are helping me spell this. I'm not the best speller, but as long as you get the idea. Okay. And so I think the best way to proceed from here is to kind of talk about the Fourier transform to follow like the historical norms. So you guys mentioned that you've seen some of these quantum topics. Have you heard of the Fourier transform? Yes. Yep. Okay. I'm seeing a lot of yeses. That's great. Then the next question would be, what does the Fourier transform do? What do you think? Yeah. So, okay, I'm seeing a lot of the right answer. So many of you, as you said, the Fourier transform is an operation that converts a function from the time domain to the frequency domain. And so what this means, this function here, this pure sine wave right here, is measured, it could be anything. So it's measured in the time domain, this x-axis, but this could be a plot of it could be a plot of pressure waves. So like how sound moves through air at a given time. It could be a whole range of different things, but the key point is that this is in the time domain. And so the Fourier transform, as you guys have said, transition or takes this pure wave and translates it into the frequency domain. And this will be W omega. And since this is in seconds, then this frequency would be in hertz. Okay. And so, you know, many of you may have seen this, but you may ponder like, what's the importance of this? If I see this pure sine wave, then I can kind of, let's say like this was so since this is in hertz, we can measure like this point here where t equals 1 second, and we can count the number of points here. So we see that it's 5. And then we look here at our frequency domain and we see that it's around 5 hertz. So you may think, what's the point of having this Fourier transform if I can just go ahead and count the frequency of my wave? And that's a very good point. But the reason why we do this is if you imagine for a second that these pure waves are a combination instead of just a single wave. So take, for instance, this plot here. I've modeled what this pure wave is, like the frequency of this pure wave right here. And so you can see that even if I have two very simple waves, when I combine them, the result is a lot more complicated. And so it may not be immediately clear what the frequency of this combined wave may be. So now the question is, can the Fourier transform somehow reverse this process of mixing these waves and so that we can see the individual components of the frequencies? So that's kind of the key idea. Okay. So maybe I can take a second here and answer a couple of these questions, such that we can kind of build our foundation for this. So if you guys have questions, let me go ahead and link them in the chat. So why is the frequency a range and not exactly 5? Is it uncertainty? So truthfully, I kind of lied to you. In fact, it should, so for this pure wave, it would exactly be 5 hertz, right? Because there's nothing else here. But when I've plotted this, I've connected this plot so that it's continuous. So instead of it just being a straight line, you see this kind of spread out wave. What's the first part? How is the Fourier transform related to the Fourier series? So in fact, it is pretty much the Fourier series. It's just like a special case of the Fourier series. So, but I won't really get into that. But they are closely related. So what is the use of the Fourier transform? So it's exactly as stated. It's to take a complicated wave that looks like this and translate it back into its frequency components. Can you tell us exactly what X and Y is in the frequency graph? Okay. So yeah. So the Y-axis is the frequency. And this X-axis is the frequency. So it tells us how often this wave oscillates in a specific period of time, in this case, a sec. And so the y-axis, why it's not labeled, is that it kind of corresponds to the magnitude. So how closely does it align with the frequency of this hertz? And so if I ran this sine wave for a longer period of time, this y-axis would grow larger because the magnitude is, I guess, magnified is the best way to say that. Okay. So those are good questions. I think what would really help you is if we kind of tried to understand what the Fourier transform is doing geometrically. And so if we want to understand what the Fourier transform is doing, we need to first look at, or sorry, well, in order, sorry, so I got ahead of myself. So before I even get to that part, this is all in the assuming that we're taking this time from negative infinity to infinity. And as a consequence to our own mortality, we don't have the time, we don't have access to infinite time. So instead, what we do is we utilize this thing called the discrete Fourier transform. Or instead of looking at the continuous sine wave or any kind of wave, we look at discrete points on this wave. And so our input is modeled here. And what this input corresponds to are these y values at certain instances. So say, for instance, this instance, x equals 0, we would have this y value here. For x equals 1, we would have this y value here, and so on and so forth. And so what's really important to note is that these are evenly spaced points on this graph. And what the Fourier transform does is it takes these evenly spaced points and it transforms them into that frequency graph that I showed you initially. And the way that it transforms it is via this equation right here. Now, this equation may not make a lot of sense when you look at it, but it's actually quite simple. So we're going to kind of go and break it down into the individual pieces so we can kind of understand geometrically what the Fourier transform is doing. And so the best place to start with here is that we have this exponential raised to some imaginary number. or complex number, really. And anytime you have an imaginary or an exponential raised to a complex number, it's good to look at Euler's formula. So I'm going to give you guys a brief refresher here. But Euler's formula states that anytime you raise e to a complex number, you get a point on this complex unit circle. So for instance, let's say that we wanted to model the point when phi is equal to pi over 2. So let's go ahead and do that. So phi is equal to pi over 2. So this part here, actually, let's do it from the top. This part here models the x, the coordinates of the x component, and this part here models the coordinates of the y component. And because this is on the imaginary axis, we'll have this factor of I on this vertical axis. And so when we solve this, we'll see that the cosine of pi over 2, of pi over 2 is going to be equal to 0. And then the sine of pi over 2 is going to be equal to 1. And so since we have this on the vertical axis, we multiply by I. And so our point for phi equals pi over 2 ends up being exactly right here. Okay. So I'm looking at some questions. What is c to the n? So this just is saying that these are real values. So the best way to say it, these are like integer values. So we're indexing from 0 to n, where n is the length of this list, or 0 to n minus 1. And so this is a list of length n. Yes, exactly. So yes, C can be complex numbers, or these values can be complex numbers, excuse me. Okay. So now that we've kind of established this unit circle, it's good to also understand that this phi kind of tells us how we move across this unit circle. So from this point to here, we've moved exactly pi over 2 radians. And notice, since this is a positive value, we're moving in this counterclockwise direction. Okay. So knowing this, we can now look at this, we can now look at the discrete Fourier transform and kind of understand a little bit of what is going on here. So this first part that I want you guys to look at is that this e to the I times a number corresponds to a point. Anytime you see e to the I or times some number, you know that it's representing a point on this unit circle. So even without knowing what this value is, you know that it's representing some point on this unit circle. Now, this negative, let's look at this next part. This negative, oops. This negative 2 pi times, and I'm going to separate it here, k over n. So we saw last time that a factor of pi over 2 moved us a quarter of the way across this unit circle. So when we go 4 quarters or a whole, then we get 1 full revolution around this unit circle. That means that this complex exponential has a period of 2 pi. Okay, sorry, I'm looking at these questions. So someone asked, can I explain the circle again? So yeah, this is kind of the second explanation. So we calculated what phi was for pi over 2. And we saw that we ended up a quarter across the circle. So we looked at the x component and we looked at the y component and we realized that this y component is multiplied by I, so we have to scale it. And so when we moved a quarter, we realized we moved pi over 2 radians. And if we go 4 quarters, we'll have to go 2 pi radians. This means that if we go a full quarter, we'll end up in the same place, and thus we can conclude that our complex exponential has a period of 2 pi. So to say that again in another way is that in order to get back to where you started, you need to move 2 pi radians. And so if we go back to the Fourier transform, or at least the discrete Fourier transform, we see this factor of 2 pi. And so that's telling us that we're going to be rotating or moving around the circle a whole revolution. Now, the direction of this revolution is changed. It's negative here. So instead of rotating this way, we're going to be rotating this way. Now, finally, I said that this complex exponential has a period of 2 pi, but now we can actually scale it by a specific amount, this k value, this k over n. So k is an integer as well as n, and we specify k by this index, or we specify what we're talking about by this index here. So we're basically taking steps around this complex unit circle. So let me go ahead and do this. Oops. So erase this here. So I'm taking steps around this complex unit circle at discrete points, at rates of this, a fraction of this. So it's going to be at very discrete points. And so what we call this the frequency. Because it kind of limits or it modulates how fast you're moving across this unit circle. And again, I'm specifying this very consistently, but this is at a very specific point where k is equal to some number, or sorry, this rate is k over n. And so now we can talk about j. What is j here? So j is an index, right? But it's indexing the specific time steps that we saw in our input value here. So j is corresponding to each of these indices, 0, 1, all the way to n minus 1. So what this is saying is that at j, let me also erase this really quick. So what it's saying at j equals 0, we can take the sum. So j equals 0, we're at the point 1. And then from j equals 0 to j equals 1, we move exactly negative 2 pi k over n radians across this unit circle. So j is basically just our time step. It keeps track of where we are for each value. So it's an index, but it acts as like a time step. So pseudo time step. So from j equals 0 to j equals 1, we move exactly negative 2 pi k over n radians. And from j equals 1 to j equals 2, we move another negative 2 pi k over n radians. So I see a question that's really important to highlight. So they asked, from j equals 0 to j equals 1, do we finish an entire rotation of the unit circle? And the answer is no. So this just modulates how fast we go around the unit circle. So there's nothing stopping us from going around the unit circle a whole revolution and end up somewhere else, maybe slightly off so they don't end up in the same place. And in fact, we'll see why that's important, because if I go back a little bit, if I kind of erase this, we'll see that this sum here, or before we get to that actually, it just modulates how fast we go around this unit circle. And so we have a good way of kind of like spacing out our points around this unit circle at certain time steps. And then when we multiply this spacing by our xj term, which is the value of y at that specific time step from our original equation, our original plot. So if I write here, xj, what this is doing is it's scaling these points in accordance to the original graph. So it kind of acts like it's winding the function around this unit circle. So winds function around the unit circle. Okay, this is circle. It's hard to write near the edge of the screen. So what this has the effect of doing, if I write it out, is now that we have these steps, we multiply it by our function, it's going to look the same as if we had our original function, say it was this, and we're just going to kind of wrap it around this unit circle. And so, as you can tell, it looks very chaotic. And in fact, that's kind of the point. It is very chaotic, except for specific, oops. So it's very chaotic except for specific frequencies. So if we go back here, we'll see that this sum kind of tells us, effectively what it's doing. So it's summing up all the points after you've scaled them to see where this where the maximums lie. So if you have a very chaotic graph, you'll see that these kind of line up, and so this will give you a value when you sum it. Some of these will kind of constructively add to one another. Some of these will kind of destructively add to one another. And so the magnitude you'll get will be very low, close to 0, if you're just looking at this. But in a very specific case, you'll get a graph that looks like this. And so the magnitude, at least in the x direction, will look something like this. And so, oops, you'll get a spike here. And so just to kind of formulate what's going on here, or at least to say it in more layman's terms, what DFT is doing is it's geometrically wrapping around a function around the complex unit circle and then adding those values to one another to see if these if the signal interfere, or if it constructively interferes with itself or not. And in the case that it constructively interferes, then we know that it's because it has a frequency of k over n. So anytime you don't have that frequency, you'll get a low value, and anytime you do have that frequency, you'll get a high value. And that's why DFT gives you those peaks at specific frequencies. This is exactly why. Okay, So I know that was a lot. So let's kind of pause here for a second and take some questions. Okay, so let's see. So I think this is a question. So the philosophy behind the introduction of DOT was the approximation to the continuous. Okay, so I think this is a question of why DFT is an approximation to the continuous, the continuous Fourier transform. And so, yes, it is an approximation. And the way it works is that the more points that you have, the closer you get to the true, I guess, resolution of the curve. So increasing n will give you a better, I guess, estimate of what these frequencies would be. But in lieu of that, you'll still be able to kind of utilize the geometric representation of the Fourier transform in the discrete case, as we can see here. Typically, what is the size of n? It can vary. So it depends on the use case. I've seen like n could be whatever you want as long as it's finite. Yeah, someone said just the size of your data set, exactly. So if you measured, let's say, like a sound wave for a second, then you could have n be the amount of uh time in between, 0 to a second if you sampled that many times. If you sampled 500 times in a matter of a second, then that would be your n. Okay. Can you explain the formula, the J part again, and about the peaks you mentioned? Please go over. Okay. Yeah. So here's the best thing. So let me just rephrase the part. So for the J part, okay. Sorry, this tablet is kind of wonky. So remember, and this is really important because this will come up later, especially. So remember that our x vector here is a series of points. And so I can label these points by having this indice here, x0, x1, all the way to n minus 1, where n is the total length of my vector. And so what J is telling me is that when J equals 0, I'm referring to this point. When J equals 1, I'm referring to this point, where J equals 2, and so on and so forth, all the way until I get to J equals n minus 1. And so it's just a way of accessing the information at that specific point in time. That's what J is representing. But when I go over the sum, now instead of just representing a single point in time, I'm looking at a collection of points over time. So instead of just looking at when J equals 1, I'm looking as J equals 1 changes to J equals 2. And then so on and so forth. As J equals 2 translates to J equals 3, right? I take a step here, another step here, and another step here. And I keep going all the way until I hit my final time step. So I may cross the original starting point, or I may not. But what's important is that when I sum these terms, do the values constructively interfere with one another, or do they cancel out? And this is what the Fourier transform is asking. Okay. So, sorry, for the interest of time, let's kind of keep going. So that was the quantum Fourier transform. Or sorry, that was the discrete Fourier transform. Now we can look at the quantum Fourier transform. And so here is the quantum. So this is our quantum. And this is our discrete Fourier transform. And so you can kind of see some of the similarities, but I guess what's more interesting is to point out the differences. And so this first difference is that we have a normalization constant here. And what this is kind of referring to is that since you have a quantum state, you need to make sure that any operation that you do on that quantum state remains on the surface of the Bloch sphere. And so having this normalization constant ensures that you map from one state to another quantum state. The next big difference, so I'll just make normalization constant. So the next big difference is that we have this positive 2 pi as opposed to this negative 2 pi. And so what this is telling us is that instead of rotating clockwise or counterclockwise, we'll be moving, sorry. So this one moves counterclockwise. Now the quantum one will move clockwise. And so both the quantum Fourier transform and the discrete Fourier transform map the computational basis to the Fourier basis. It's just that the direction in which they do it is opposite. So the quantum Fourier transform, or maybe I should say it the other way, the discrete Fourier transform is actually analogous to the inverse of the quantum Fourier transform and vice versa. So hopefully that collects. And so we have this geometric representation of the discrete Fourier transform. It still applies to the quantum Fourier transform, but the difference in inputs is that we're mapping from the computational basis to the Fourier basis. Other than that, geometrically, it's doing the same exact thing. Okay. So we can map this quantum Fourier transform in the form of a unitary matrix. And so instead of acting on just a singular value of y here, we're going to define a matrix. So let's take, for instance, the 1 qubit case. So 1 qubit. So it's important to know that when we're talking about qubits, our value of n is the number of computational basis states, which is equal to 2 to the power of the number of qubits. So in this case, it's 2 to the 1. And so now we can fill out the rest of this equation. So 1 over the square root of 2 times n minus 1, so 1, from j equals 0 to the sum of n minus 1 to k equals 0. And we can finish by saying e to the 2 pi I jk divided by 2 k j. And so as we expand this, we see that anytime that j or k is equal to 0, then this exponent, or this exponent will be equal to 0, and thus our value will be 1. So when we write that out, we can write it as this sum, 1 over the square root of 2, is equal. So we'll do 0, 0. So we know the coefficient is 1. So 0, 0, plus 0, 1, plus 1, 0. And then when both of these values are 1, we get e to the 2 pi I divided by 2. So that's e to the pi I. And e to the pi I is equal to -1 if we look on our complex unit circle. Because remember, when we rotate pi over 2, we get, if we go back here, if we rotate pi over 2, we get I. If we come back down here, we get -1. And I'll let you guys prove that to yourselves. So we get this. And so if we add this up, we'll see that we get this equation here. So it's 1, 1, 1, -1. Yeah, over the square root of 2. And this may look like a gate that you guys have seen before. Do you know what this gate is? Yes, exactly. It's the Hadamard gate. So what we've done is we showed that the Hadamard gate is actually the 1-qubit quantum Fourier transform. So that's pretty cool that every time you've been using the Hadamard gate, you've actually been utilizing this quantum Fourier transform. So to prove this to ourselves, that this is in fact the Hadamard gate, and I'm not just lying to you, we can write effectively the same equation, but instead of as a unitary matrix, we can write its action on a state. So if I go ahead and say that I want to apply this for the 1-qubit case once again, so 1-qubit, we know that our n is equal to 2 to the 1. And so if I expand this equation as I act on the state, so I'll say QFT over 2 on my state J is going to give me the sum of n minus 1, which is 1, from k equals 0, e to the 2 pi I k, or sorry, jk over 2. So we can expand this sum that I'll write here. So it's equal to, when k is equal to 0, so when we have this 0 state, this coefficient will be 1, so we have 0, plus when k is equal to 1, we'll have the rest of this exponent. So we have t to the 2 pi I. This is 1, so now we're looking at just j over 2. So I'll keep it there for now. And so this is the result of applying our quantum Fourier transform. Oops. Yeah, this is the result of applying our quantum Fourier transform to this computational basis state. Now, J can have the values of 0 or 1, right? So it's going to be, so when J is equal to 0, so this means when we start in the 0 state, and when we apply this quantum Fourier transform, we're going to get 0 plus J equals 0. So this value will go down to 1. So we can write this as applying QFT to the 0 state, and we get this value. When we apply QFT to the 1 state, we'll get, again, 0. But now we have a 1 here, so this is e to the pi I yet again, so it's -1. And this is just the plus state and the minus state. So these are what you get after applying a Hadamard. So we've shown, and frankly, the same way that the quantum Fourier transform is just the action of applying a Hadamard to a state in the one qubit case. But we can also generalize it to any the any qubit case. Forgot the square root of 2. You're absolutely correct. So there is a square root of 2 everywhere here to keep these normalized. But I digress. Yes, yes, there should absolutely be a square root of 2 right there. Okay. But the point is, we have a general form for what this quantum Fourier transform should look like for a system size of any n, where n is again equal to 2 to the power of the number of qubits. Okay. So this is kind of wraps up the quantum Fourier part. Were there any questions for this? So kindly go over QFT2 again. So is it this matrix part that you were hoping to see again, or is it more so this or the whole thing? Okay, and then while you type that, someone asked, why do we go clockwise in DFT and counterclockwise in quantum? Does the difference have any physical explanation? And the answer is no. I believe so. This is me extrapolating. I actually don't know this for sure, but I believe the reason that we do this is because of historic reasons. When Peter Shor kind of introduced this concept, he made it so that it was easier to work with in this positive basis as opposed to uh, going in the opposite direction. So they have both effectively accomplished the same thing. It's just, if you look back here, whether you go the full circle or half a certain movement around this way or half a movement around this way, you get to the same place. That's kind of the idea. It's just a matter of preference at that point. And so since we stick with it historically, this is kind of what the definition has become. Okay, and then I see the question, no, the Hadamard part again. Sorry. Proving H is the QFT. Okay, cool. So let's just look at this unitary matrix again. So if we plug in our value of n for 1 qubit, and this is how we get n, we see that we can write this summation right here as 1 over the square root of 2 from 0 to n minus 1, and n is 2, so this is 1, to k equals 0 to 1. And then we have this exponential right here. So e to the 2 pi I j k over 2 times the outer, or yeah, multiplied by the outer product of your input and output. Or I've set that backwards, your output and input. And so anytime that you have 0, we see that since we're multiplying j times k, anytime either of those values are 0, then this entire expression becomes 0, and so e to the 0 becomes 1. So when we write this, we'll see 0, 0 in our outer product, but the exponent will be 1. And since this is a sum, we add them together. So 0, 0 plus 0, 1 plus 1, 0. Now, when j equals 1 and k equals 1, this exponential no longer is 0. Or I guess 1 in this case. So we plug in the values of 1 and 1, and we find that this comes down to e to the pi I. And e to the pi I is actually just the value of -1. And we know that by looking at our complex unit circle here. So we multiply this 1 state by -1. And then when we add these values together, we get this Hadamard expression. So hopefully that should help. Okay, so what is exactly the relationship between QFT being related to the Hadamard gate and DFT? Like, can we visualize DFT taking us from the time domain, the frequency domain? So how can we think of QFT having the same properties of a Hadamard? So what we've just done is that we've defined the Hadamard gate. So it's no longer is relating the Hadamard gate to QFT. It is a quantum Fourier transform. So it maps this computational basis, as we see here. It maps the computational basis into this Fourier basis, and we can represent this Fourier basis based on these values here. So the Hadamard gate has the effect of doing exactly what the quantum Fourier transform should do. Is the QFT usually visualized using the unit circle, or do we use the block sphere? So you would usually use the block sphere, but so I don't have really a slide for this. But think about it like this. Since you're looking at so the plus and minus states are no longer in the z basis. So it's going to be on the plane of the x and y coordinates. And if you look at a slice of that sphere, it becomes a circle. And this is why looking at it from this unit circle perspective is effectively the same as looking at it on the block sphere. Okay. So if we have more questions, we can come back to this, but I think it's important to talk about this, why we were looking at the quantum Fourier transform in the first place. And so getting into it, the quantum phase estimation, we can kind of define the problem, not even kind of, we can define the problem as so. So given a unitary, and emphasis on unitary, quantum operator U, and access to one of its eigenstates, so this is an eigenstate, can we efficiently estimate the corresponding eigenvalue of U? And so you'll notice here that I have this 2 pi I theta here. So remember that a unitary matrix has a magnitude of 1. So typically you'll have this be your eigenstate, or sorry, your eigenvalue. But we kind of want to estimate theta. And so in order to do so, we need a unique value of theta. And to ensure that we get a unique value of theta, what we do is we scale this initial phi parameter by 2 pi in a fraction. So in our fraction is, I've written this terribly. So we're going to scale this phi by 2 pi in a fraction, theta. And so what this does is that we can kind of conclude that when we look at theta, we're going to get a value from, so theta is going to be contained in a range from 0 all the way to 1. And so I've written this way to show that we're going to include values of 0, but not include values of 1. The reason being that this complex exponential has a period of 2 pi. So if we included 1, we would end up in the same position as if we ended up with 0, right? Because that would correspond to a full revolution around the circle. So now that we kind of have an explanation of what our theta value is, we're going to use an n-qubit phase register to kind of encode this approximation of theta. And so our qubits will be in binary, so our approximation to theta will have to follow this equation. Oops. So we're going to approximate theta by the binary fraction of y over 2m, where y is equal to, or it's really contained in the set of, I don't know why this isn't working. It's contained in the set of 0 to 1 dot 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 to n minus 1. Oops. Okay. And so what this really means is that we're going to use this register to represent the value of theta, and this theta will be in binary. And so it's always going to be an approximation via this value right here to what the true value of theta really is, because you may not be able to represent the true value of theta with m bits, or at least a finite amount of bits. Okay. So to kind of talk about the importance, or before we go into like the bigger description of phase estimation, let's talk about this phenomenon known as phase kickback. Okay. And so what we're going to do is, instead of, we're going to utilize the information that we have. So we have a Hadamard gate, and we have a unitary, and its corresponding eigenstate here. So we can implement a controlled unitary by making sure that each of the gates and that define the unitary in and of itself has a control. That will make it so that anytime that the state is 1 up top, we'll apply all the gates in our unitary, and anytime it's 0, we apply none of them. So we can kind of let's take a look at what happens as we progress through this circuit. So I'm going to label these. Actually, let's do it up top. So I'll have what the state looks like here. State looks like here, here, and here. So we'll start with 1. So at state equals 1, we have our eigenstate psi tensored with our initial qubit. So far so good. Nothing's happened. Now we're going to apply the Hadamard to our first qubit. And so I'm going to condense this notation just a little bit. So we'll have psi actually, let me write this differently. So I'll factor this out. So 1 over the square root of 2, parentheses, are psi plus this Hadamard. So it's going to be psi 1. And then we finish the parentheses there. So after we apply the Hadamard, we've gone into the plus state where it's still tensored to our original state psi. Now we apply the unitary only if this initial value is 1. So we only really apply it to this. And if you remember, when we apply the unitary, we're going to get, since this is an eigenstate, we're going to get some phase or some eigenvalue here, and we're going to get our psi back. And this psi is going to be equal to, or this lambda, sorry, is going to be equal to exactly what we defined here, e to the 2 pi I theta. Oops. So e to the 2 pi I theta. So if I write that here, we'll have 1 over the square root of 2. So nothing happens here because this initial qubit is 0. Plus this unitary here. So I'm going to simplify it and just write out our e to the 2 pi I theta here. And then we'll have, I have to kind of move this a little bit. So, oops. We'll move this like so, just a little bit over here. So we have this, and then our state psi over 1. Okay. And then so we're going to finally apply the Hadamard again. So let me just check my notes here. Okay. So this is good. Once we do this, cool. So we're finally going to get this state. Just double checking notes. Aha, okay. Good. It's going to be this state here. So I'm going to factor out this psi. So or actually, let's do it this way. So I'll factor out the psi again, just so you can see what happens. It's going to be tensored with 1 over the square root of 2. And it's going to be 1 plus this value, e to the 2 pi I theta. And then, oops, I've written this wrong, actually. I'll just expand it out normally. This is going to be tensored with this, 1 plus e to the 2 pi I theta divided by 2, minus, or plus, actually. And this is on the 0 state. And it's going to be plus, and I'll just write it on the second part, 1 minus e to the 2 pi I theta over 2. And so these are our coefficients for the 1 state. So these are coefficients for the 1 state at this point in time, briefly before measurement. And so after we measure, we can plot what's going to happen as a function of theta. And so our probabilities are going to be those coefficients squared. So I'll write it out for you. So P0 is going to be equal to the absolute value of our 0 state, the complex exponential, 2 pi I theta over 2 squared. And our P1 is going to be equal to 1 minus e to the 2 pi I theta over 2 squared. Okay, pull this back up. Okay. And so, okay, I see some people were kind of confused. So what we've done is we looked at how the state is transforming over time. So we applied the Hadamard to this initial state here. We looked at how that splits this first qubit, this top qubit, into the plus state. Then we applied the unitary to only when the qubit is in the state 1. So that's only in the state 1 here. And once we do that, we apply the second Hadamard, which I've kind of simplified for you and told you that the state that you get back is this, where it's 1 plus e to the 2 pi I theta squared. And so this is our coefficient for the state. Finding the probability of this state is as simple as squaring this amplitude, or taking the absolute value and squaring this amplitude. And so since this is still a function of theta, we can plot these probabilities as you go from 0 all the way to 1, where this value of 1 is exactly equal to this value of 0. So it shows that you complete a full rotation around your complex unit circle. So looking at this, let's say, for instance, that we were guaranteed to have a theta that was either 0.5 or 0. Well, when we measure our circuit, we'll know exactly which theta we'll get because we'll either get 1 with full probability, or we'll either get a value of 1 or we'll get a value of 0. Sorry, we'll either get a value of 0 or we'll get a value of 1. And depending on which value we get, we know which theta that we have. So this is good, but it's not great because we'll see here that if our estimate of theta isn't exact in this case, so say we're not guaranteed to be on y equals 0 or this theta or theta equals 0.5, then we'll have some kind of mixed probability in this region. So it's good, but it's not great. So let's see what else we can do. So instead of only applying the unitary once, let's see what happens when we apply the unitary twice. And well, like I'm going to rewrite this again. So if we apply this unitary to our state psi, we get some lambda back in our state psi. So if we applied it a second time, so u squared, we should get back a second application of our lambda. And so what this is really going to do for us is that our lambda is going to be equal to e to the 2 pi I times 2 theta, because we've multiplied by this additional factor of theta. And so what this has for us is that we're going to double our frequency. So instead, where we only oscillated once, we're going to oscillate twice. And so let's say, for instance, that again, we're promised that theta is going to be a value of 0 or 1/4. Well, then we'll know exactly which one it is based on our measurements. If we get back a 0, then we know that our theta is 0. Well, we may know, we think it's 0. Actually, sorry. If we're promised that theta is 0 or 1/4, if we measure 0, then we know that it's 0. And if we measure 1, then we know that it's 1/4. But this isn't strictly better than the first case because we'll see here we have 2 peaks. So if theta was the value of 1/4 or 3/4, we wouldn't be able to distinguish what our theta is. So the point of this is that we can extract more information by applying the unitary multiple times, but this isn't strictly better than applying it once. So the whole goal of applying the unitary is to figure out our information about theta. We're trying to figure out what could the value of theta be. Okay. And so finally, what happens if we combine the two approaches? So we can kind of go through the same process as we did before, where we look at the state prior to these prior to applying these gates. Okay. And so in the state, so at 1, after we applied both Hadamards to this gate, or sorry, so after we applied both Hadamards to this state here, we can write it as you write this down here. So 1 is equal to our state psi, and it's going to be tensored with the sum, the double sum of a equals 1 to 0 to 1 because A is the value of this this qubit here, and we have a qubit, so it's gonna be, we're only gonna increase it by 0 or 1. So A equals 0 is equal to, actually, perhaps I should write this with a little bit more space. And so we'll have 1, 1 here. And this is going to be our state A0 or A1, A0. And this is multiplied by the factor of our normalization. So let me just do that just a little bit. Get rid of this. This is 1 over the square root of 2 tensored, or sorry. So I'm already forgetting. This is our value of n, so it's actually the square root of 4 there. Oops, 1 over the square root of 4. Okay, I just double check what that is. Okay, oh, it is the square root of 2. Okay, good. And then the square root of 2 of 4 is 2, so we can simplify that. Okay, so now we can write out this part after we apply the first unitary to the first qubit. So again, in the interest of space, I won't be writing this psi anymore, but keep in mind that it's still tensor to the rest of this. Okay, so we can simplify our scalar value right there, and then I can apply this unitary to only this first qubit, so A equals 0. And so when I do that, I get 1/2 times the sum for A equals 1 equals to 0, sum A equals 0 equals 0 from 1. And then I get that phase factor that I talked about earlier. So e to the 2 pi I theta, it's multiplied by A0. And then we get our state back. A1, I really don't have enough space for this. So A1, A0. So this is the point after applying this first unitary. Well, what do you think happens when we apply 2 unitaries to the bottom qubit? So we get 1/2 our state, A1 equals 0, A0 equals 0, and 1, 1. And we get e to the 2 pi I, parentheses, theta, parentheses, 2A1 plus A0. It's just not enough space. A0. And this is, again, applied to our state here. Okay. And so we see here that we can rewrite our state, since this is just a binary register, we can write this in terms of an integer. But we can also write this summation after applying these two states, because it's 2 times A1 plus A0, where A1 and A0 are binary bits. So I'm going to rewrite this final state here after 3 and a little bit more clearly, so it'll make more sense. So it's going to be 1/2 the sum of, let's call this binary number, or this integer, x. And it's going to be from x to n minus 1. So we know our n is 4, so it's going to be to 3. And it's going to be e to the 2 pi I theta x. Okay, and this is going to be acting on our state x. So now we've written the form for what the state should look like after we apply these two controlled unitaries, or after we apply a sequence of unitary controlled unitaries. So we haven't measured yet, but this is kind of give us some intuition behind what's happening. Okay, so that was kind of a lot. Let's maybe take a step back here and look at some questions. So let's see. So it seems like you guys are pretty good on this. I see someone said they weren't able to connect the slides. Okay, well, I mean, just to give like a brief overview of what happened. So we were looking at a phenomenon called phase kickback. And so we wanted to see what would happen if we applied our controlled unitary to this Hadamard state. And we found that when we did that, we could see that we get a state with these kind of probabilities. And these probabilities are tied to theta. And we can see that once this is how they look. And now we say that if we were promised that theta could be one of two values, if theta could be one of two values, whether it's 0 or a half, we would be able to distinguish which ones they are based on the measurement that we did here. So if we measured the state 0, then we would know that our theta is 0. But if we measure the state 1, we know that because this has a probability of 1, we know that our state or our theta should be 0.5. And so we looked how this happens in succession when we applied multiple controlled unitaries, and we see that we increase the frequency. And when we increase the frequency, we're able to tell that, we have a little bit more options of what theta could be, but it's not strictly better than the previous one because we have some overlap, right? So we have 2 peaks here with probability 1 as opposed to just 1. So it kind of narrows the range of what theta could be, but we can't decipher whether theta is this value or the difference between theta in this case. And so finally, we kind of controlled the two, or we've combined the two approaches, and we were resulting in this state here, where we see that the probability or the state that we get back is a function of theta still, and this integer value that we defined by this binary encoding. And so if we look at the special case for when y is equal to 0, 1, 2, or 3, right? Oh, this didn't format correctly. So this is when theta is guaranteed to be some value of y over 2 to the m, so y over 4, for y values of 0, 1, 2, and 3. So theta is guaranteed to be one of these values. Okay, I see a good important question. So how are we finding eigenvalues since our main goal is to define eigenvalues? So that's a good question, and we're going to come to that. But let's look at the special case, because this may help realign everything for everyone. So if y can only be one of these 4 values, we can find what y is by looking at this equation here. And this is what we defined right here. So this is the sequence of applying these gates. So we know that if we do this, we can do this for phi. Oops. So we'll do this for y equals 1. So phi equals 0. Oh, sorry. So we got 1/2 over the sum. Actually, let's expand the sum itself. So when phi is 0, or this y value is 0, and we see that theta is equal to y over 4, then that means this exponential will always be 1. Or the value of this exponential will always be 1. So as we scale from 0 to 3, it's going to be the state 0 plus state 1 plus the state 2 plus the state 3. So we can do this for everyone. And what's interesting is that, well, I'll come back to it in a second. We can do this for all of them. So let's do it for this one. So when 2 pi, so at x equals 0, this will always just be 0. But when we move to this next state, we'll have 1 times 1. So this equates to, we divide that by 2, so it's pi over 2. So the value is pi over 2i. And we remember that pi over 2 is this value here. So we can say that this is going to be I times 1. In fact, this one will be -2, and this one will be, move this a little bit. This will be -2. And this will be -i. Move it a little bit there. Be -i3. So we can do this for all of them too. And notice, cool thing here, that how we're moving across this unit circle. So for this one, we moved a full revolution each time. This one, we're moving only 1, so a quarter. Now we're going to be moving, or I guess we didn't move at all, is the best way to say this. So we didn't move at all. Now we're moving a quarter. Now we're going to move a half. So this is going to be 0. This is going to be -1. This will be +2. Or I did this right. Just double check. Yep. Okay. So this will be +2. And that should be -3. So we're moving. So we started with moving a quarter. Now we're moving a half. Now we're going to be moving 3/4, which is in fact the same as just moving backwards by 1. So on this unit circle. So it's 1/2 here. We start with 0 state. We get -i1. This will be -2. And this will be +i3. Okay. And so what this is saying is that given that y could be any one of these choices, is there some way for us to distinguish them from one another? So that's kind of the key question that we have here. And the answer is yes, because these 4 states form an orthonormal basis. And in fact, if you paid any kind of special attention, we know exactly which basis this is based on this exponential. It's the Fourier basis. So this means that if we have some unitary matrix that maps us from the Fourier basis back to the computational basis, then we can extract the value of y that we want. And we do. We defined that earlier. This is the quantum Fourier transform. So if we apply, since we're already in the Fourier basis and we want to go back to the computational basis, then we're going to need to apply the inverse quantum Fourier transform. And so here I've kind of written out what the quantum Fourier transform is, just so you can refresh your memory. And so looking at it, right, you can see the similarities of the state that we get from applying our controlled unitaries in our quantum Fourier transform. And so in the special case, so let me rewrite what I said, or maybe I can say it like this. In the special case of when y is guaranteed to be integer value of 0 through 3 for 2 qubits. This is the same as defining the QFT for n equals 4. So QFT for 4 on some state, let's call it x, is going to be equal to this phi state here that we get here in the special case. Actually, instead, let's call this y. So tie this back. Okay, so this means that if we apply the inverse of the quantum Fourier transform, so Q dagger for our state phi, we're going to get back our state y with some coefficient here. And the reason why we get it back is if we applied the quantum Fourier transform here, these would kind of cancel out and we're left with some coefficient here. Okay, so to recap everything that we've done, we've applied a sequence of controlled unitaries that mapped us into this Fourier basis, and to map us back into the computational basis, we're going to apply this quantum Fourier transform. And so in the event that theta is guaranteed to be an integer value, so remember, we're approximating theta. Theta is approximated by y over 2 to the m, where m is the number of registers that you have in your circuit. So in the event that y is one of these exact values, then we're going to get the exact answer for theta. But you'll see here that what I'm saying is that when you're guaranteed to have, y equals 0, y equals 1, y equals 2, or y equals 3, you see that we get the full probabilities with the associated curves. But oftentimes we're not guaranteed to have theta here, or theta is not guaranteed to be one of these values. There's no restriction on what theta can be in between 0 and 1. But in the special case, we know that we'll get these exact values like this, and we can plot the probabilities as so. So this is what you get after applying the quantum Fourier transform. So if you apply the inverse, it's this negative sign here, and then you factor out your theta value and subtract it. And so this is what you get here. And so you can see how this kind of scales as you have these different peaks here. And so this is really good. So if we're guaranteed to have one of these values to be an integer value of y, then we know exactly which one it is. And again, the same way, if we measure 0 and we're guaranteed to have one of these y values, then we know that when we measure state 0, our y must be equal to 0. And if our y is equal to 0, then we know that our theta is equal to 0, and so on and so forth. If we measure 1, then we know that our theta should be 1/4. If we measure 3, then we know, or the state 2, we know that our theta should be 1/2. So hopefully that makes a little bit of sense. And we should see what happens when we increase the quantum register, right? So we're not guaranteed to have theta be any one of these values. This is just a special case. But when we increase the number of quantum registers, we'll increase the number of peaks. And so we'll have, in fact, 2 to the n peaks. But just to show you how this relates to what we were doing before, I've only included the first 4. And as you can see, these peaks kind of get much narrower. So if we looked at what it was before, in fact, it got twice as narrow. So we squeezed our precision of what theta can be by increasing the number of registers. And so you can see that here, it's the square root of 1/8 instead of the square root of 1/4. It's a factor of 1/8 instead of, it should be the square root. So what we've proven here is that increasing the number of registers increases the precision in which we can measure theta by a certain amount. But what you'll notice is that we kind of have this overall limit. In fact, let me measure this with this. So we kind of have this overall limit of how precise we can be. So in the case that our true value of theta is exactly in between these values, these peaks here, our worst case is that, measuring the state 0 or measuring the state 1 is equally likely. And so this is our worst case scenario. And this is our bottom limit. And there's like a proof that you can show that you'll never get worse than around like 40% probability of measuring that state. So kind of to summarize the whole idea of what we're doing is that we showed that increasing the number of registers increase the precision in which we can measure theta, but it doesn't increase the probability of measuring a certain state. And that's a key distinction to make here. This probability that we will measure a certain state will always be greater than 0.4% for the closest estimate of theta. So if theta is close to 0, then we'll best get, or at worst, we'll get a measurement of 0 with about 40% probability. And likewise for state 1. Now that we know that, we can kind of take this on and see kind of what happens when we generalize this to the actual phase estimation algorithm. We kind of know all the pieces to the puzzle at this point, so it's just a matter of plugging them together. And so this is the general procedure of the phase estimation. You'll see that we follow the same idea that we did in the 1 and 2 qubit cases, where we apply a Hadamard just before applying our unitary. And so for an m qubit register, we'll apply m many Hadamards, and we'll have actually this value here. So we'll apply u to the 2, or u squared m minus 1. So the amount of unitaries that we need as we increase our precision of our register here increases exponentially. So this is like a big cost with phase estimation. And in fact, it's a major limiting factor for why this isn't used more often. Phase estimation is kind of restricted by this exponential cost and the amount of times that you need to apply this unitary. So, but for a small number of m, phase estimation works great, given that you have relaxed the precision that you need to achieve with your theta estimate. And so after you apply your controlled unitaries, you apply your inverse quantum Fourier transform to map your circuit or your state from the Fourier basis back into computational basis so that you can estimate your theta. And I mean, that's generally how phase estimation works. So hopefully what we've done, which is kind of a recap, hopefully we've kind of built an intuition of how the Fourier transform works, both geometrically and mathematically. We've related it to how quantum Fourier transform is supposed to perform, doing the same operations, but in on a computational basis state instead of the time domain. We looked at how phase kickback is, a phenomenon utilized by phase estimation, and how we get those, how we get to the phase, or how we get to the Fourier basis by applying this phase kickback. And then we've kind of estimated what our theta should be, i.e. phase estimation, by applying the inverse quantum Fourier transform to this phase kickback phenomenon. Okay, so I know that was a lot, but I think this would be a good time to take questions over that topic. We can kind of wrap up here.
Perfect. Yeah, thanks a lot, Jeremiah. This was indeed a lot for everyone to digest. We are already over time here, but yeah, I didn't want to interrupt you before, since I saw a lot of activity on Discord, and I assumed, even though we are 10 minutes over time, more than like 250 participants are still tuned into your lecture. So yeah, I'm assuming they have had a good time listening to this lecture. How about we take another 5 minutes to quickly go over any additional questions that you might have, and otherwise, yeah, feel free to put the questions on Discord. Jeremiah is also on Discord, so he can pick up your questions and answer them.
Yeah, okay. I see this question. Are there like any additional resources on QFT and I assume phase estimation? And the answer is yes. There's a lot of resources on phase estimation and the quantum Fourier transform. One that I specifically recommend is Qiskit's explanation of phase estimation. In fact, this is where I got a large amount of my figures from and kind of followed the general methodology, but they explain it in much more rigorous detail. I kind of kept it at a superficial level, showing plots, but they'll go into deeper about the math and why things are the way they are through proofs. So I definitely recommend looking at the Qiskit documentation for the Fourier transform and phase estimation. And I see, yeah, of course, I'm happy I gave the talk, and I hope that you were able to take something away from this. In fact, if I had to request you to take anything away from this, it's just simply the fact that the Fourier transform, sorry, there's like a lot of slides in this deck. The main thing I want you to take away is that the Fourier transform converts a function from the time domain to the frequency domain. The quantum Fourier transform does the same thing, but it maps the computational basis to the Fourier basis. And phase estimation in general just comes as an artifact of this phenomenon called phase kickback. And so if you understand those three things, then they'll set you up to kind of explore this topic in much more detail. Okay, so I'm not seeing any more questions right on, so it's maybe a good time to maybe try to go back to schedule.
Sure. Yeah. We can start wrapping up here. Thanks a lot, Jeremiah. And with that, maybe we can wrap up the session. We also have Abhinay here with us. Abhinay, do you have any final words before we wrap up?
Yeah, thank you so much, Jeremiah. This was a great session, very useful, and you went over it so carefully, and we really appreciate it. Thank you for taking the time, and I'm sure our participants really appreciate it as well. Thank you so much again.